So, hello there, and welcome to lesson 14 in our study of optimization 2. So, in this lesson, we will learn how to solve an unbalanced transportation problem. Okay, so in our previous videos, we've been talking about the transportation problem, but we were dealing with the one which was balanced. So, when you have an unbalanced transportation problem, how do we solve it? Okay, and aside that, we also learn about one or two themes. So this video is going to be very helpful. Okay, helpful. So far in our study of transportation problems, we have only dealt with balanced transportation problems. So when the model is unbalanced, how do we go about that? So what is an unbalanced transportation model in the first case? So an unbalanced transportation model occurs when either the demand exceeds supply or supply exceeds demand, right? So when we have one of these cases, then it means that our model is unbalanced. And mostly when we have an unbalanced, always when you have an unbalanced transportation model, we try to balance it first before solving it. And we balance it by adding either a dummy row or a dummy column, depending on whether demand exceeds supply or supply exceeds demand. Okay, so if demand exceeds supply, then we add a dummy row to the table. And if supply exceeds demand, then we add a dummy column to the table, right? So yeah, in reality, the dummy cells are what we call slack variables, right? Just like from when you start solving using a simplest algorithm, you know what slack variables are. So let's take an example. Say example one. So let's consider when demand exceeds supply. And we said when demand exceeds supply, then we are going to add a dummy rule. Let's see how to go about something like that. So let's consider the problem below. Alright, so this is the supply. Alright. So the supply from Kansas City is 150, Omaha 175, Demwa 275. So the total supply is 600. And this is the demand. Chicago 200, St. Louis 100, Chicago 350. So the total demand is 650. So for instance, when you have a place where you have machines and they can supply these quantities, and these places need these demands. So you want to transport the goods to these cities, and you want to know how to do it to make sure that the transportation is minimized. But you can see that the supply here is 600 and the demand here is 650. So here demand exceeds supply. So when you are solving this problem, it will be unbalanced, right? But you have to balance it first. So we do that by adding a dummy row. Now before that, the cost involved in transporting the goods are what you can see here. So from Kansas City to Chicago is, I think this is Cincinnati, is $6. From Kansas City to St. Louis, $8 and the rest. I hope you understand that. All right. So this is how we are going to draw our initial simplex tableau, right? So you can see that from 1 to A, from 1 to B and the rest, right? We are going to use the cost that we have here. So with the problem itself, when we draw the tableau, this is what we are going to get, right? But you can see that here the supply will be 600, but the demand is 650. So what we do is that we add an additional row, which we call the dummy row. And the dummy row has cost of 0. So all the cells will have a cost of 0, right? So that from the dummy row we can have an additional supply of 50. Then when you add it to 150 plus 275 plus 175 plus 275 plus 50 will give you the 650, and the demand 200, 100, 350 will give you your 650. So before you can solve the problem that we did, you have to add a dummy row to balance the model. Then you solve this using a normal procedure that you know, right? So example 2, what if supply exceeds demand? So we are going to use the same data from question 1, right? So with the same data from question 1, now let the supply to Kansas City be 250, right, instead of the 150. So you are letting this be 250 instead of the 150. And if you do that, now the supply is going to be 700, which exceeds demand, which is 650. So to rectify this problem or to solve this, we are going to add a dummy column, right? So when we are drawing our simplex tableau, you can see we've added a dummy column here, right, which has cost of 0 throughout, and we have a demand of 50 here, so that when you add everything here, you get 700, and the model becomes balanced. So this is how we will balance the model before we solve it, right? So let's just take a typical example. But before that, let's talk about some terms. But we will take a typical example, okay? So sometimes in solving our transportation model, we can encounter an issue known as degeneracy. So in a transportation tableau with m rows and n columns, there must be m plus n minus 1 cells with allocation. If not, it is degenerate, right? So in a degenerate tableau, not all of the stepping stone paths or modal equations can be developed. So to rectify a degenerate tableau, an empty cell must be artificially treated as an occupied cell, right? So this is what we are talking about. I'm illustrating it here for you. So you can see that with this question that we have here, we have 3 rows and 3 columns, right? So that means that to make sure the issue of degeneracy does not exist, we must have 3 plus 3 minus 1, which is 5. We must have 5 allocations. But you can see that here we have just 1, 2, 3, and 4. That means that since we have 4, which is less than 5, there is degeneracy. So mostly when you are trying to solve this problem using the stepping stone path or the modified distribution method, it becomes very difficult to get a stepping stone path. So we artificially make an assignment to any of the empty cells, the one which is going to guarantee that we are going to have a stepping stone path, so that we can be able to use the stepping stone path or the modal to solve our problem, right? So it says the tableau shown in this table does not meet the condition, because this is the condition, right? Because there are only 4 cells with allocations. And it says the difficulty resulting from a degenerate solution is that neither the stepping stone method nor the modified distribution method will work unless the preceding condition is what's met. So when a tableau is degenerate, a closed path cannot be completed for all cells in the stepping stone method, and not all the ui plus vj equals cij computations can be completed in the modified distribution method, right? So for example, a closed path cannot be determined for the cell that we had there. So to create a closed path, what we do is that one of the empty cells must be artificially designated as a cell with an allocation. I've said all this already. And blah blah blah. So we choose that arbitrary. So you can see that now when we put 0 here to create an artificial location so that we can calculate what the stepping stone path. So now we've been able to artificially make our problem not degenerate. Then we can use the stepping stone path or the modified distribution method to solve it. So note, when you are always solving a problem, note the issue of degeneracy can occur. And if it occurs and you don't correct it by doing an artificial location, then you use your stepping stone path method and modal, but you're not going to get any result. Okay. So note that the cell in which you do the artificial location matters, but there is no way about it. Okay. So sometimes we can have what we call prohibited routes. Alright, so a prohibited route is assigned a large cost, such as M. We use the same concept as our big M, right? So that it will never receive an allocation. So sometimes, why we do that is that sometimes one or more of the routes in a transportation model are prohibited. That is, units cannot be transported from a particular source to a particular destination. So when this situation occurs, we must make sure that no units in the optimal solution are allocated to the cell representing this route. So in our study of the simplex tableau, we learned that assigning a large relative cost or a coefficient of m to a variable would keep it out of the final solution. Yeah, right, using the big M method. So this same principle can be used in a transportation model for a prohibited route. A value of m is assigned as a transportation cost for a cell that represents a prohibited route. Thus, when a prohibited cell is evaluated, it will always contain a large positive cost change of m, which will keep it from being selected as an entering variable, right? So, for instance, let's say with this problem, if from supply 1 to this city, right, this source to this destination, if let's say there is a transportation problem there and that route is prohibited, that means instead of this 100 here, we'll assign a large cost of something like 100 so that it will be possible. So that the large cost of 8 here, we are going to, the cost here is 8. We are going to assign a large cost of m, very large one, so that there won't be any allocation there. Okay, so that's what we're trying to say. And you can meet all these issues when you are solving transportation models, so you have to be careful. So now let's learn how to solve an unbalanced transportation model, right? So the question says solve the following transportation problem. So for KNUC students, this is an example in the lecture, your lecture notes for this particular course. Okay, question 4. So it says solve the following transportation problem, right? So there's a, they've given you this tableau, but let's look at something. When you add the demand, that is 1050 plus 500 plus 650, you get 2200. And when you add all the supply, 800, 500, 600, it gives you 1900. So you can see that they are not equal and the demand exceeds supply. So that means that with this question that we have here, it is unbalanced. And before we can solve this unbalanced transportation problem, we first have to balance it. So here the demand is greater than the supply. So in balancing it, what do? We are going to add a dummy row, right? So this is what we are going to do to balance it. So we have the dummy row here, all right, and we would have a supply of 300 here, so that now when you add all the supply, you also get 2200, and this model becomes balanced. So now that it is balanced, now we can solve it, right? Okay, so when you're solving transportation problems, we solve them in two different phases, right? So in the first phase, we try to look for a basic feasible solution using either the Vogel's approximation method, the northwest corner method, or the minimum cell cost method, or the least cost method. So let's find a basic initial feasible solution using the least cell method or the minimum cell cost method, right? So okay, I think let's do it here, then you see what we did over there. So you can see that with the least cost method, we try to make allocations in a cell with the minimum cost, right? So you can see all the cells here, the one with the minimum cost is 0. Okay, right? So when it comes to this place, for instance, we can make an allocation of 300 here, And when you make this allocation, you can see that the supply constraint is met, right? So that means we wouldn't have to make any allocation here again. So after here, we ask ourselves, what is the next smaller one, right? You can see that is 10 and 10 here too. So when it comes to this 10, right, we can have a supply of 500 here and a demand of 650, but already we've covered 300, so we can put 350 here. And when you do that, it means, so here this is met, and here too it means this demand constraint is also met. Then when it comes here we can put all the 500 here, and this will be met. It will be left with 300 to be put here, right? So after the 500, the next one can have 15. So with the 15 too, we have 1050 here, but we need 500 here, which we've already assigned 350. So that means the maximum we can put here will be 150. And oh, what happened? So I think this place is 20. Okay, this place went away. So this place went away. So this is 25. All right. So that means this part is also satisfied. So we have 150. Then we need to satisfy. Okay, so here to be assigned 500. So this place also satisfied, right? Because we all have all the 500 here. But when it comes here, we need 600. And the 600, we can only put it here. So we put our 600 here. And when you put our 600 here, we are still going to get 750. We need 300 more. So we put the 300 here. And now you can see that we've been able to do all the allocations. And you can see we have 4 rows and 3 columns. So we have 7. So 7 minus 1 is 6. That means there has to be 6 allocations to make sure that we don't have the issue of degeneracy. So let's see that. 1, 2, 3, 4, 5, 6. So you can see that, right? So that's the table, the cell that you can find here. So this is the same thing as what I did, right? So oh, no, I made a mistake, right? We've already done an allocation here. Okay, with what I did, we already done an allocation here. So that means that this 300 should have been here. Or if we had brought it here, then this 300 would be here, right? So sorry for that, but the concept is that you look for the cells with the minimum cost and you assign as much as possible over there, right? So you can see I did this in a different way, but you can also do it in a different way as well. And that's how I did mine here. And when I did that, the minimum cost was $31,000, right? So after doing this, the next thing for me to do is to check to see if the solution is optimal by using a stepping stone method or the modified distribution method. So I'm going to use the modified distribution method to check optimality, right? So that means I'll have to develop the equation. So this is how we develop the equation. It is ui plus uj is equal to cij for the allocated cell. So when it comes here, for instance, saying this one is allocated, you are going to have u1 because we have 1 here plus v1 will be equal to 40. That's for them to be u1 plus v2 is equal to 10 and what have you. So doing that, we are going to have these equations, which are the modal equations, right? So we mostly solve them by assuming u1 is 0. So when u1 is 0 from here, then v1 will be 40. And if v1 is 40, it means u4 will be minus 40. And if u4 is minus 40, then we can have, if v1 is 40, then we can have u3 to be minus 20 and what have you. So solving the system of linear equations, you're going to get these equations here. Then would have to calculate what we call the net cost change. In the net cost change, we calculate it for the empty cells, and we use what we call Kij equals Cij minus U1 Ui plus Vj, which is the same as Cij minus Ui minus Vj. So you can see that here we have an empty cell here. So that means here the net cost change is going to be K21 will be equal to C21 minus U2 minus V1, right? And that will give us minus 15. So we'll calculate for K22. Since K22 is also an empty cell, we calculate for this, that, this, and that. So we'll calculate for all of them. So when we calculate for K22, we will get 20. K32 will get 35. K33 will get 30. K42 will get 30. And K43 will get 20. So you can see that all the values that we had were positive with the exception of what? K21. So it means that since we have a negative value here, the table that we had is not optimal, right? So we have to do an iteration, right? So we say we can see that K21 has a negative cost change. So that means our solution is not optimal. So we have to draw a stepping stone path for that cell. So this was that cell, right? K21. So I'm drawing a stepping stone path for it. If you don't really get this, then try to watch the previous videos on the stepping stone path and the modified distribution method where we really talked about them in depth. Okay, so this was a cell which was um negative, so we draw what we call a stepping stone path for it. So we start here and we draw the stepping stone path for the cells using the cells with allocation. So we go here saying there is an allocation here, and since we start here, this is positive, this is minus, so that it nullifies the effect in that column. Now one will saying is here, so that this plus and minus also nullify that, and this also saying is here, so that we have the plus minus nullifying out. So this is going to be the stepping stone path for the cell x21, right? So that means to move from s to 1, you first have to go to x11, then you go to x13, you go to x23, then you come back to s21. So the second iteration, what we are going to do is that, you see, this is a stepping stone path that we used, and this place was plus, this place was minus, this place was plus, this place is minus. What we do is that in the next iteration, this 150 here, we'll bring it here. Then since we have minus here, it's 150 minus 150, then we will not have any allocation here. Then this 150 to, you can see we have plus here, so we add 150 here, and this will give us 300. And since we have minus here, we'll subtract 150 here, and this will give us 350. So in the next allocation, we are going to get this, right? So after getting this, you could see that the cost has been minimized to 28,750, which is smaller than the 31,000 that we have here. And we calculate the cost by 500 times 10 plus 300 times 20, what have you. Then you get to 28,750, right? So now we have to also check and see if this table is optimal, right? And to do that, we have to use either the stepping stone path or the modified distribution method. And I like using the modified distribution method a lot. So we would have to develop the modal equations, and by now you should know how to develop them, right? So developing the modal equations, you get for instance u1 plus u2 equals 10 and what have you, right? Then you find the net cost change. So I say use the modal method to check for optimality, and you find out that all the cost change values, that's Kij, are positive, hence this solution is optimal, right? So please complete it by developing the modal equations and calculating the net cost change, right? All of them should be positive. because this solution here is optimal. So thank you very much. That's going to be all for this video, and I'm sure you've really learned a lot. So in the next video, um we are going to talk about when you have a special case of a transportation problem. Some of the transportation problem, you can be asked to maximize the objective function. So when you have a maximization transportation problem, how do we solve that? So see you in the next video.